Okay, so next what I want to talk about is using this binary search tree to also perform select operation. Remember, basically the select problem is that you're given a set of nodes, you want to select the elements with order k, with specific order statistics, like select the median and so on, okay? And in describing this, I'm also going to introducing the idea of augmenting a data structure. And in this specific case, we're going to augment a binary search tree, okay? So what do I mean by that? Okay, now, say we want to handle the select operation. What does it mean? That means that given a key k, given an order k, okay, a rank, and we want to, and a tree node x, okay? So this tree node would store a bunch of keys in the tree rooted at x, okay? We want to consider all the numbers stored there, okay? We want to return a node whose key has order k, okay? So for example, if k equal to 0, if k equal to 1, that means that I want to return the minimum of all the elements inside there, same as the minimum operation we talk about, okay? And if k equal to n, that means we want to return the maximum, okay? Of course, the tricky part is that what if k equal to n over 2? So you want to find the median among all the numbers stored in this tree, okay? So how do we do that efficiently? Okay, so that's a question, all right? And now, clearly, I have this tree here and all the numbers are stored inside. I could just somehow visit all the tree nodes and search for this key, okay? So we can do linear search and then implement the select operation in linear time, okay? But that's kind of slow. The question is that, can we do better? Okay? All right. Now, let's see why the binary search tree can potentially help us, okay? And what do we still need with this? So here's a binary search tree, okay? Let's say that suppose I'm looking for the median, okay? So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 13 numbers, okay? So let's say that I want to look for the rank. So we want to do select. I want to select for the number, which is 7. Okay, so how do I do that? Okay, now we're at the root. To look for this order, so here the order 7. Okay, we want to look for the median of all the numbers stored here, namely the number whose order in the sorted array, if you sort all of them, will be number 7. Okay, so to know where to go, whether we go to the left or go to the right, it would be nice if we can somehow know that how many numbers we have here. What do I mean by that? So suppose someone tell you that, oh, there are altogether 1, 2, 3, 4, 5, 6, 7, 7 numbers to your left. And there are 5 numbers. So here the number size is 5. And here the size is 7. So if someone gives you this information, okay, and they are looking for the number whose order is 7, okay, whose rank is 7, you're looking for the order statistics with rank 7, then you can actually make a decision. Why? You know that if there are 7 numbers to my right, to my left, that means that the 13th itself, the order of this root 13 is in fact 8. It's 7 plus 1. So I am in the 8th position because there are 7 numbers smaller than me, right? And I look for the one with order 7. That means I'm looking for someone who's smaller than 13. So in that case, that means I need to go to the left, okay? And then repeatedly, if someone gives you this information, then you can repeatedly decide where you go, left or right. Okay, so in this case, now I'm looking for rank 7, but now someone tell me that, oh, there are 3 to my left and 3 to my right. That means that my rank here will be rank 4. And I'm looking for rank 7. Now it means I'm looking for someone who's bigger than 6. So now I go to right. Okay, so if this size information was given to me by some oracle, then I could actually do a search procedure in this tree to look for the elements with a specific order statistic with order 7 in it, for example. Okay, but where do I get the size information? Okay, so the approach we're going to do is that before we perform select operation, I want to augment my binary search tree data structure so that I can have the size information to support this operation efficiently. Okay, so the specific information we're going to augment is, as I mentioned, the size information. Okay, but before that, let me just point out that once we have this augmented size information, it turned out that we can then perform the select operation in the same time as the search, namely, the time is order of height of the tree. And if we use balance the binary search tree, the height is always log n, then we can do it in a big zeta of log n time. Okay, so to perform select. Okay, once we have this augmented information. All right. Now, the information that we want to augment, as I said, is the size information. So at every tree node now, I'm going to add a new entry. And remember that. I'm going to record that in the tree node. I'm going to also store the so-called size of the tree, which is simply the number of nodes in the subtree rooted at this node, including X itself. Okay, and if the node is a leaf, if a node, sorry, not leaf, if a node is nil, is a null node, then its size is 0. Okay, a leaf node, the size, if a node is a leaf, then its size clearly is 1. It only have one node in subtree. Okay, all right. So here's an example by the information. So here, my key, just because I want to reduce confusing, here, these are the key stored in the tree. In other words, the keys I'm storing here are A, C, D, F, all these letters, okay? Here, this is the size information. Okay, so for example, at the root node, my size is basically total number of nodes we have in the tree, which is 9. Okay, and at this node, whose key is C, the total number of the size of the subtree rooted here is this subtree, and there are 1, 2, 3, 4, 5. That's why it's 5 here. Now A is a leaf, so I don't have any children. The subtree has only one element, which is myself. So the size is 1. Okay, F has size 3, and so on. So these are the information that I would like to also store in my tree. Okay, and this called augmented. So this is a binary search tree augmented with size information. Okay, so it's an augmented binary search tree. Okay, all right. Before we talk about how we're going to use this to, the idea of using this to answer a select query, how do I set up this information? When, if I give you a binary search tree, how you now also add the size information, okay? And to do, note that the size information doesn't change the space complexity of the tree because I only add a constant extra memory to each node. So in total, the space of this binary search tree is still only linear space, okay? All right, to help us to find a procedure to augment a binary search tree with the size information, okay? So here is one fundamental property of the size information that's useful. It's a very simple property. It says that the size of X, so if I have a node X, okay, and here I have the left, this is X, left, the left child, here I have the right, So this is x dot right. Okay, so what this says is that the size of x equal to the size of its left subtree plus the size of the right subtree plus x itself plus 1. Okay, and the size of the left subtree is simply the size stored at its left child. Okay, so this is basically, let me write it, this is size of left subtree of x. Okay, so this quantity. And this quantity is size of right subtree of x. Okay, so the size of x equal to the size of the left subtree plus the size of the right subtree plus x itself plus 1. Okay, so it's a very simple property. Okay, why is this property useful? Well, what this property tells me is that if I know the size of my subtrees, I can then compute the size of x itself. Okay, so this suggests that I can set up the size information of all the nodes in the tree by a bottom-up process. Okay, so in particular, here's what we have. The algorithm is a simple recursive algorithm. Okay, let's see what it's doing. So yeah, so here I'm assuming that if a node x is nil, then its size is 0. Okay, so what are we doing? To given the tree rooted at x, okay, now let's first recursively set up the size information for everyone in the left subtree. Okay, so recursively set up size info for all nodes in left subtree. And then here, I just recursively set up all the size information for all the, so I'm here, and I have the left subtree and the right subtree. I first call this one to recursively set up everyone, all the size information for everyone here, okay? Then I call this function to recursively set up all the size information for all the nodes in the right subtree. Once I have both of this, what is my size? My size simply equal to the left subtree size plus the right subtree size plus 1. That's it, and I return. That's it. Okay. So I didn't put explicit termination, the base case here, because I assume that if x is nil, then we return 0. Okay. This is where to return, because if x is nil, I go to this line, so I return 0. Okay. So very simple recursive algorithm to using the property of the size to set up this information. Okay. How about the, so for those of you who know, you may have seen this. This is so-called post-order traversal of the tree. A tree traversal is basically a way to visit all the nodes in the tree. Okay, so this is called the post order because I first visit my left child, then I visit my right child, then I visit myself, me myself. Okay, so I do this post the order of the children. That's why it's called post order. Okay, there's also so-called in order and the pre-order. Okay, so this is a post order traversal. How much time does it take? Again, it will be hard to write a recurrence relation for this, even though this is a recursive algorithm. Okay, but again, we have to think globally. Okay, we try to think that, okay, how many times are we going to visit some nodes? Okay, then what we see is that, well, within each of this, we'll visit a node and then we'll then go to its either left child or right child, right? So the time that we're going to visit each node is exactly once. Okay, we're going to call this this function on each of tree node exactly once. Okay, and the other time is only constant other than recursive calls. So it means the total time that we're going to make this recursive call is actually bounded by the number of tree nodes, which is the size of the tree. So if there are n tree nodes, this is basically theta of n. Now, you cannot do this in better time, say log n, because here you really need to visit every tree node once, but exactly once. That's why it's order of n. Okay, so we can set up, what we said is that we can set up the size information to augment our input binary search tree in time, in linear time. And the resulting binary search tree still have the same linear space complexity, okay? Finally, once we now have this augmented information, how do we now perform select operation, okay? I will not give you the pseudocode for the procedure, but I'm going to first explain the idea behind, okay? You have a homework problem later to realize this idea in the real algorithm, okay? All right, let's say that suppose I want to select the element with rank 3. So here, let's assume that the order of all so our key is letters, okay? Let's see that it's alphabetically ordered. So the smallest one would be A. That's basically, then the next one is C, the next one is D, then the next one is F, H, M, P, Q, T. Okay, so that's what we have. So we want to look, the ordering, the ordering between them is the alphabetical order, okay? So the element with rank 3, with order 3, really is D, because that's the third smallest number in all of these keys. The third smallest key among all these keys stored here, okay? So how do we do it? We start at the root, okay? We say that the root, how do I know that whether let's first ask, what is the rank of the root, okay? The order of the element M is in fact, basically, I have 5. I look at the left child. There are 5 numbers there, elements there. That means that there are 5 keys smaller than me. So the order of M is basically the size M dot left dot size plus 1, which is 6. Okay, because I have 5 elements smaller than me. So my order is 6. I'm the 6th smallest key among all the keys. Okay, all right. So I first compute the order of the root, and that's 6. And I'm looking for 3. So that means that I'm looking for an element smaller than the root. That means I should go left. Okay, now we're at the left. We're still looking for the rank 3 element. Okay, so now I'm at C. I say that what is the order of C? Well, this equal to the order, this equal to the left child size plus 1. And there's only one, the left child size is 1. That means there's only one element smaller than me. So I am order 2. I'm the second smallest number, okay? But we are looking for 3. That means that now I have to go to the right, okay? So I'm going to go to the right. All right. So far, we're still looking for the one of order 3. However, now, note, I'm looking for order 3 here, the third smallest among the entire subtree, okay? Now, when I move to the right, I'm looking for the number 3 in the entire subtree, but when I go to the right, I actually already eliminate 2 things that are smaller than me, okay? So what I'm looking in this subtree now is the rank 1, the smallest one, okay? 3, because they're already 2 smaller than me, so now I'm looking for 3 minus 2. I'm really looking at the smallest one now, okay? So here is the important thing. So here we're looking for, in this subtree, the rank of the number we're looking for is 1, because it's 3 minus 2, okay? So we're here, and I'm looking for the order, the smallest element within the subtree. Now, the rank of F, again, by the same token, the order of F is basically the size of D plus 1, which is 2. And I'm looking for the one with rank 1. So I need to go to now the left. Now, there's only one element here. So I am the rank 1 element. So we found it. So we return. This is the idea of the procedure. Okay, questions? Okay, so if I need to just quickly, if I need to look for the elements with rank 7, I do the same. I'm here, I know that the order of M is 6, and I'm looking for rank 7. That means that I need to go to the right. Okay, however, in the right subtree, I'm looking for the 7th smallest number in the entire tree. But if I go to the right, I only have part of the array. The rank I'm looking for now is really 7 minus the order of M. Because these are all the elements smaller than me that I already throw out. So I'm looking for the number 7, smallest number. That means I'm looking for the smallest one within this right subtree. And here I'm looking for the smallest number. And here my right side is actually 0. That means my rank in this right subtree is 1. That means that we simply return P. Okay? All right. So let me, in fact, just go with one more example to hopefully make this more clear. So let's say I want to select the number, select the one with the order 9. Okay, so while here, this one is order 6. That means that I need to go to the right. But within the right subtree, now I'm looking for rooted at P. Now I'm looking for 9 minus 6, which equal to 3 now. So I'm looking for rank 3 within the right subtree because I already found 6 smaller than me. I throw them out. So instead of the 9th smallest number, now I'm looking for the 3rd smallest number within this restricted right subtree. Okay, so I'm looking for the rank that's 3, but the rank of P is 1. That means I need to go to the right again. Since now I have 1, so within this part, let me use a different color. Now here I need to select within this subtree, which is the subtree rooted at T, but I'm looking for size, which is 3 minus 1, which is 2, because this I have one number that I eliminated smaller than me, that's equal to 2. Okay, so now I figure out that the order of this, I have 1 to my left, so the rank of the T is 2. So we simply then return T. This is what we have. Okay, all right. So this is the idea behind the algorithm. As I said, that this can actually be easily implemented using a recursive algorithm. Okay, using the idea that I just described, because as you can see that we basically have to go either left or right accordingly, depending on the rank we're looking for with the order of the current node we're inspecting. Okay, so how to implement this will be a homework problem. Okay, but the time complexity of this procedure that we described is in general the height of the tree, proportional to the height of the tree. The reason is because you are simply following a specific tree path, whether you go left or you go right. Okay, so the length of the tree path is bounded by height of the tree. So if you're going to use a balanced binary search tree, then the select operation can be done in log n time each time. Okay, so earlier we talked about that if you have an unsorted array, you can do select in linear time. But if you have them now already organized in the binary search tree, then you can balance the binary search tree, then you can select any rank, any order statistic in log n time. Okay, and you can also update this list of numbers. Okay, all right. As I said, how to implement this to give this time complexity using recursive algorithm, because what described is easiest to describe using a recursive algorithm, will be in the homework. Okay. Okay, so that's all that I want to say today. Let me just mention that, in fact, we're not completely done, because we talk about, given the binary search tree, how to augment this binary search tree using post-order traversal to augment the size information. But I have to be mindful that if you have dynamic change of the tree, like under insertion and deletion, your tree structure changes, so the size information will change. Okay, then you have to also update all this augmented information as well. Okay, but fortunately for the size information, this can be done very easily. Okay, Another remark is that you may say that, oh, but if I don't use a binary search tree, I just organize all the array in a sorted array, then I can select a specific order statistic in constant time. Why do I bother with the binary search tree? Well, the reason is because an array does not support dynamic operation. Again, the whole reason that we want to go to binary search tree versus just using an array is because a binary search tree can support dynamic updates, insertion, deletion efficiently, which array cannot. Okay, so that's why using the augment binary search tree is a better data structure in this case. Okay, right? So this is just one very simple example of augmenting data structures. In practice, actually, sometimes you can, given some data structure, say maybe a tree, sometimes the actual information you want to augment at each node can be very complicated. It can be, in fact, a separate tree data structure here. So you're going to associate another tree to each of the node here. Okay, so a lot of efficient data structure, including those that for databases to support the range queries, actually have this very complicated augmented data structure. Okay, but we just give a very simple example, right? Okay, all right, that's all that I want to talk about today.